Today, we're diving into one of those papers that just makes you go, aha! It's a paper that took a core idea in deep learning and completely flipped it on its head. And it's all based on a simple, almost backwards-sounding concept that led to some of the most efficient and powerful neural networks we've seen. So this is the big question the whole paper revolves around. And you have to admit, it feels wrong, doesn't it? Your gut tells you that adding more connections, more wires, is just going to make a network bloated and slow. But these researchers asked this wild question. What if the exact opposite was true? What if cramming in as many connections as possible was actually the secret to making a model that's both smaller and smarter? All right, so to really get why this idea was so out there, we need to rewind a bit and look at the huge problem that everyone in the field was stuck on. You know, for the longest time in deep learning, the mantra was simple: deeper is better. If you wanted a more powerful network, you just added more layers. It makes sense, right? More layers can learn more complicated things. But as these networks started getting crazy deep, we're talking over 100 layers, researchers slammed right into a wall. And that wall has a name: the vanishing gradient problem. The best way to think about it is like that game of telephone you played as a kid, or maybe making a photocopy of a photocopy of a photocopy. Every time the information passes through another layer, the signal gets a little bit weaker, a little more garbled. And by the time you get to the end of a super deep network, that original crucial information is basically gone. And if the signal is gone, the network just can't learn anything. And then a really brilliant solution came along that kind of broke through this wall. It was a new type of architecture called a residual network, or ResNet for short. And honestly, this was a game changer that let networks get truly, truly deep. The big trick ResNets used was something called a skip connection. And you can literally think of it as an express lane on a highway for your data. It lets the information from an earlier layer just skip over a bunch of the middle layers and show up fresh and clean way down the line. It was a fantastic way to fight that signal decay. Okay. So ResNets gave us these express lanes, but the folks behind this paper, Densenet, they looked at that and thought, what if we took that idea and just turned it up to 11? Now this right here is the absolute key difference. Look at ResNet on the left. It takes information from two different layers and adds them together. It sums them up. The information gets kind of blended. But Densenet on the right does something totally different. It doesn't add, it concatenates. It just stacks the information side by side. Think of it like this. ResNet mixes two colors of paint together. Densenet just puts the two paint cans next to each other. Nothing is ever lost or blended away. So what does this lead to? Well, it leads to this honestly kind of bonkers idea. Instead of just having a few express lanes, they said, let's connect every single layer directly to every other layer that comes after it. I mean, just let that sink in. A normal 100-layer network has about 100 connections. A 100-layer Densenet has almost 5,000. It's a completely different way of thinking about how information should flow. And here's how the authors themselves put it. It's so direct. Every layer gets to see the work of all the layers that came before it. This creates what they call a collective knowledge, this constantly growing treasure chest of information that any part of the network can dip into at any time. Okay, so you're probably thinking, a network with thousands of connections, doesn't that just become a hopelessly tangled mess? And you'd be right to ask, but they had a really clean and elegant solution for this called dense blocks. The logic inside these blocks is actually beautiful in its simplicity. Each layer just does these three things over and over. First, it looks back and gathers up all the feature maps from every layer before it. Second, it does its own job and creates a small, fresh batch of its own new features. And third, it passes on the whole collection, everything it received plus its own new stuff, to all the layers that come next. That's it. It's just a constant cycle of gather, create, and share. And this right here is the secret sauce. This is what makes Densenet so incredibly efficient. It's a little number they call the growth rate, or just K. Because information is never lost, each layer doesn't have to waste time relearning things that previous layers already figured out. Instead, it only has to contribute a tiny amount of brand new information. And when I say tiny, I mean it. We're talking as few as 12 new feature maps. That's it. And that is why these networks can be so unbelievably lean and efficient. So, clever architecture, elegant idea, but who cares if it doesn't actually work, right? Well, let's get to the results. Because this is the part of the story where things go from interesting to whoa. Okay, check this out. On the top line, we have a monster of a ResNet, 1,001 layers deep, totally state-of-the-art. It gets an error rate of 4.62%. Really good. Now look at the Densenet on the bottom. It actually beats that score. Not by a ton, but it's better. 4.51% error. But that's not the incredible part. The incredible part is in that middle column. So that 1,000-layer ResNet, it had 10.2 million parameters, an absolute beast of a model. And the Densenet that beat it? Just 0.8 million. Less than 1 million parameters. It got a better result with over 90% fewer parameters. That is not just an improvement, it's a completely different ballgame for efficiency. And this isn't just about model size on paper. This translates to real-world savings. On the much harder ImageNet dataset, a Densenet was able to match the performance of a top-tier ResNet while using roughly half the amount of computation. That means it's not just smaller, it's also faster and cheaper to run. It's a win-win-win. So why does this work so well? What's the lasting impact here? Well, it all boils down to this incredibly powerful principle, feature reuse. So let's just break down why Densenets really shine. First, you get this incredible feature reuse. A simple feature like the texture of a leaf that's learned way back in layer 3 is directly available to layer 90 to help it identify the whole tree. This leads to much more compact models, which also means they're less likely to overfit your data. And then you get this really cool side effect called implicit deep supervision. It just means that because every layer is so directly connected to the end goal, it gets a very clear training signal. It makes the whole network way easier to train. And the authors themselves pointed this out in their conclusion. Because these networks are so good at creating these rich, compact bundles of information, they make fantastic starting points for other computer vision tasks. You can just take a pre-trained Densenet and use its smarts to jumpstart a whole new project. And that leaves us with this final thought. For years, the race in AI was all about going deeper and deeper. But this paper really forced everyone to stop and ask, wait, what if we're missing the point? It proved that by being smarter about our connections, we could build models that were better, smaller, and faster. It really makes you wonder, doesn't it? Maybe the future of AI isn't just about being deep. Maybe it's also about being dense.